Entropy is a fundamental concept in thermodynamics and statistical mechanics that measures the degree of disorder or randomness in a system. It plays a crucial role in understanding the natural tendency of systems to evolve towards equilibrium and has profound implications in various fields, from physics and chemistry to information theory and cosmology. At its core, entropy is a measure of the number of possible microscopic configurations that correspond to a system's macroscopic state. In simpler terms, it quantifies the amount of uncertainty or disorder within a system. The concept of entropy was first introduced by the German physicist Rudolf Clausius in the 19th century and later developed further by Ludwig Boltzmann and others. One of the fundamental principles of entropy is the Second Law of Thermodynamics, which states that in an isolated system, the total entropy can never decrease over time. This law implies that natural processes tend to move towards a state of maximum entropy or disorder. For example, if you place an ice cube in a glass of warm water, the ice will melt and the water will cool down until both reach the same temperature. The system moves towards a state of higher entropy as it approaches thermal equilibrium. Entropy is also associated with the concept of irreversibility. In any real process, there is always some increase in entropy, which means that the process cannot be reversed without adding external energy. For instance, once cream is stirred into coffee, it cannot spontaneously separate back into cream and coffee without external intervention. This irreversibility is a manifestation of the second law of thermodynamics. In statistical mechanics, entropy is related to the number of microstates, possible configurations of particles that correspond to a given macrostate, observable properties like temperature and pressure. Boltzmann's formula, S equals K log W, where S is entropy, K is Boltzmann's constant, and W is the number of microstates, provides a quantitative way to calculate entropy. This formula highlights that entropy increases with the number of possible microstates. Entropy also has a significant role in information theory, developed by Claude Shannon. In this context, entropy measures the uncertainty or information content in a message. A highly ordered message with predictable content has low entropy, while a random message with unpredictable content has high entropy. This concept is used in data compression and encryption, where reducing redundancy, low entropy, can make data storage more efficient. In cosmology, entropy is connected to the evolution of the universe. The Big Bang started with a state of low entropy, and since then, the universe has been expanding and evolving towards higher entropy. This increase in entropy over time explains the arrow of time, giving a direction to the flow of events from past to future. Understanding entropy also helps explain various natural phenomena and processes. In chemical reactions, for example, the tendency for entropy to increase drives reactions towards equilibrium. In biological systems, the maintenance of low entropy states, order, requires a constant input of energy, such as food, to counteract the natural tendency towards disorder. In summary, entropy is a measure of disorder or randomness in a system and is a key concept in thermodynamics and statistical mechanics. It explains the natural tendency of systems to move towards equilibrium, the irreversibility of real processes, and plays a crucial role in information theory and cosmology. By understanding entropy, we gain insight into the fundamental principles that govern the behavior of physical systems and the flow of time.